All right, so in that last section, we actually introduced this slightly more generalized notion of an elliptic curve. So that is one of these generalized Weierstrass equations, which were built up to attack the problem of if I wanted to do some elliptic curve cryptography over one of these finite fields that happen to have characteristic 2, all of our classic elliptic curves are going to then become singular. So we needed to generalize the notion of what these elliptic curves were all about so that I could accommodate for these new fancy fields. So in this section, I'm actually going to be chatting about what these new fancy fields are all about so that we can then take these items and then shove them back into those generalized Weierstrass equations and then emerge with a massive plethora of elliptic curves, and then we'll jump back to the cryptography side of it. So we kind of do this little song and dance idea of introduce the new equation, talk about the underlying guts, we'll bring it back to the actual equation, and then build the crypto systems out of it. What's really nice about this is that once everything is set up, the jumping it back to the crypto system side is really, really easy. We can actually take all of the stuff that we've already created and just do a swap of the functions that are in play. So we're going to change out these objects to, what field I'm looking at is now going to become this field, and then you change the equation as well. So to kind of remind you of the original structure for what finite fields are all about, we've typically been living in these finite fields with p elements. So these integers modulo some massive prime p. So that is, we have the numbers from 0 all the way up to p minus 1. So if I have 7, it would be 0, 1, 2, 3, 4, 5, and 6. So what makes this world really nice is that as long as you're working with something that's non-zero, you're always going to be able to identify what the inverse is going to be. So that's one of the huge assumptions that we were going through over and over and over again. Obviously, in this elliptic curve addition algorithm, there was division all over the place. Division is simply just going to be multiplication by the inverse, and this is saying that all of those entries actually have inverses, which is totally necessary. What we want to do now is we want to broaden this idea a little bit. So we want to think about how can I construct a field that's not going to have a prime number of elements? Which pains me a little bit because I love primes obviously a whole bunch, but now I want to start thinking about how would I construct a field that has 4 or 8 or 16 or 32 or any random power of 2 number of elements in it. So we're going to make this a little bit bigger, which actually gives us a pretty big toolbox to work with. So as I mentioned at the beginning of the last video, the current NIST standards actually have this kind of smorgasbord of what elliptic curves are deemed safe, and over half of them are elliptic curves over these fancy new finite fields. So it's totally worthwhile to explore what actually makes these things tick. Once we're all done with that, we'll start to see how AES actually works, which actually makes use of some of these fancier finite fields as well, because they have all kinds of beautiful mixing properties and things like that as well. So we're going to head ourselves a little bit. So let's start chatting about how we can actually build up one of these curves, or how we can build up one of these fields, I should say. And then we'll come back to looking at curves. So to start this thing off, I'm actually going to look at a field that is going to have 9 elements in it. So later on, our big goal is to look at things that are going to have 2 raised to some k power. So I'm changing it up a little bit just because it serves as a pretty nice segue. So what's going to happen here is that I want to identify a field that's going to have characteristic 3. So that is, anytime I see a 3, that's going to be reduced down into a 0. And my goal is that this new little field is actually going to have 9 elements in it. So obviously we can't just look at the numbers modulo 9, because if I start representing those as, 0, 1, 2, 3, 4, 5, 6, 7, 8, I get bad properties happening there. Because if I were to look at those numbers, so if I had 0, 1, 2, 3, 4, 5, 6, 7, and 8. So this is these integers modulo 9. That thing is not a field. One of the big issues is that if you were to look at 3 and multiply it by itself, that emerges as a 0. And that's a huge problem. So I'm going to get some things that are going to be non-invertible. Really bad stuff is going to occur there. So the big picture here is that we need another way to identify 9 elements that are going to bring about this nice inverse property, some multiplication, all of those kind of goodies that I need to have in a field. So what's going to happen here is that we're going to be kind of cheap, and we're going to think about 9 as being a 3 times a 3, and we're going to begin looking at combining some numbers mod 3 with another number mod 3 and then merging them together. So the cheap way to do that is to bring about some complex number theory. So I'm going to define this new little object, which is going to have all of these little points of the form a plus bi. So I here is this magic little symbol that we all know and love that has the property that when you square it, it kicks out a -1. So what I'm going to do is I'm going to build this little list, which happens to have 9 entries in it. And the entries are going to be of the form a plus bi, where a and b are going to be some number mod 3. So that tells me that those little coefficients can either be 0, 1, or 2. So you can very quickly spam out what all these are going to be. So we have 0, 1, and 2. So those are going to be, a is 0, a is 1, a is 2, where I don't have the imaginary part. So in all 3 of these, we have a b, which is 0. And then I can shift it over a little bit. So I have I plus 1 plus I and 2 plus I. So those are all going to have a b, which is a 1, and I'm cycling through the a values. And then last but not least, I'm going to have the scenarios where my b's are all 2. So I'm going to get 2i, 1 plus 2i, and 2 plus 2i. So this collection of things has exactly 9 elements in it. So at least it's a start, is that I have something that appears to have the correct number of elements in it, which is great and dandy and awesome. And I have all of the standard arithmetic that I'd ever want to think about here. So this is going to go back on, I don't know, your college algebra or your algebra 2 days, whenever you first start looking at complex numbers, is that we know how to add these things together. We know how to subtract these things. We know how to multiply them. You just FOIL it all out. All of those properties are going to come back into play. So if I were to take 2 entries, so let's say 1 plus I and 1 plus 2I, if you add those together, the 1 and the 1 make a 2, and the I and the 2I make a 3I, and the 3I, well, characteristic 3, so that 3 is going to reduce down into a 0, so that term disappears, and you're just left with a 2. So it's this kind of fancy new arithmetic that allows me to create new objects and then suck itself back into this little set again. Likewise, I can do multiplication pretty easily. So if I take those 2 entries, so 1 plus I and 1 plus 2I, if I do some fancy foiling or double distribution or whatever the youths are doing nowadays, I can see that if I multiply it all out, I'm going to get a 1 plus a 2I plus an I, and then plus 2I squared. So those are my 4 terms. And then if I begin squishing some of these together, so the 2I and the I, those are going to become 3I. The I squared we know is a -1, so that's going to reduce down into a -2 when I look at 2I squared. So that becomes -2. And then I have the 1 out in front. So the 3I thing we see dies off because 3's are 0 in this world. So that thing dies. And I'm left with 1 minus 2, which is a -1. But again, we're in characteristic 3. So -1 is the same thing as a +2. So all of the arithmetic is going to constantly be bringing me back to these numbers 0, 1, or 2, and then maybe I add an I or a 2I afterwards. So if I multiply those 2 things together, it properly returns a 2. Which is kind of a cute fluke here, is that the sum of those 2 points adds up to a 2, and the product of those 2 things add up to a 2. That's not always the situation, is that if I add things, I might get something crazy, and if I multiply them, I might get something else. So they're not always going to be the same. That's just a weird consequence. It is worthwhile to at least just run through the arithmetic of one row of a multiplication table. So if you were to think about making a giant table that has all 9 entries across the top and all 9 entries across the bottom, what I'm going to do is I'm going to begin multiplying these terms all out. So that's what I've done here, is that I have all 9 entries across the top. And then I'm just going to multiply everything by 1 plus I. So it gives me a little bit of practice of how this arithmetic's all about. And it is also going to show me some of the important characteristics of what's actually going on here. So 1 plus I multiplied by 0 is boringly going to make a 0. 1 plus I times a 1 is boringly going to make a 1 plus I. So I say boring, but those are actually important facts. So the 0 is going to be this notion of this thing that if I add 0 to anything, it's always going to bring me back. So it's this additive identity. And the 1, which is going to be the important entry here, is going to be this notion of this multiplicative identity. So if I multiply anything by a 1, I'm going to go back to where I start. If I add 0 to anything, I'm going to go back to where I start. So this field has both a 0 and a 1 in it, which is important. So next up is if I were to take 1 plus I and multiply it by 2, well, the 2 distributes in, so I boringly get 2 plus 2i, which is cool. If I multiply 1 plus I by an I distribute the I across, so I get I plus I squared. The I squared obviously becomes a negative 1. The negative 1 then becomes a positive 2. And if I write this as 2 plus I, you can see that it is properly going to be one of those entries in that list that I started with. 1 plus I, if I square that thing or if I multiply it by itself, so I do the foiling process, so I get 1 plus 2i plus I squared. The I squared obviously a negative 1. The 1 and the negative 1 here actually turn out to be a 0. You could also see that as negative 1 becomes a positive 2, and 2 plus 1 makes a 3, and 3 is 0. So in any bit, that's going to reduce down into a 2i. The next bit is 1 plus I and a 2 plus I. So if you FOIL that thing out, you get an I plus a 2i in the middle, which turns out to be a 0. The I squared is going to become a negative 1, and 2 minus 1 is a 1. So the big kind of exciting red underlined thing there is that that's going to tell me that 1 plus I and 2 plus I are actually inverses of each other, which is exactly this little factoid down here. Inverse is important. Obviously, when we come back to building these fancy little crypto systems and doing this addition algorithm, we have to know how to divide. Division is inverses. So now we know that that thing actually has an inverse, which is important. Okay, so next up, if I take 1 plus I and multiply it by a 2i, again, distribute. Anytime I see a negative 2, that becomes a 1, so that returns 1 plus 2i. The 1 plus I and the 1 plus 2i, we actually multiplied before, so we see that it still returns a 2. And then 1 plus I and 2 plus 2i, if you do the fancy distribution, we end up returning with just this little I. So the thing to note here is that in this giant big multiplication table, on that particular row, what's going to happen is that if I multiply all of those entries by 1 plus I essentially just reshuffle the deck. I get all 9 entries back, they're just in a different order, which is exactly what I want to have occurring in these fields, is that I want to think about multiplication with random entries as shuffling things around. You can see that there's going to be some security embedded in there, is that it's kind of a mysterious shuffling. There's just some weird flinging of things about. When I couple that with an elliptic curve, it makes for even some crazier shuffling. So we're constantly just taking horrible entries and making them worse, and then making them even worse and worse and worse by getting all kinds of random mixing properties in play. So that's all that's happening here, is that this is one row of this multiplication table, which we can properly see is going to return every single entry that I would like to have, which is super awesome. So we have this field that happens to have 9 elements, which is great. The downside here is that if I were to try to do this with a field that wants to have 4 elements, so this is me transitioning back into, well, how can I define a field that's going to have 4 entries? If you would try to do basically the exact same thing that we just did. So I'm going to make this little list of 4 entries. So A plus BI, where A and B can either be 0 or 1. What ends up happening is you get exactly 4 things. You get 0, 1, so those are happening when B is 0, and you're going to get I and 1 plus I. Those happen when B is a 1. If you build the multiplication table for those 4 entries, it seems pretty awesome initially. So the row of 0 is obviously dumb because 0 multiplied by anything is going to kill it off. The row for a 1 is also kind of dumb in that it's just going to return whatever you're multiplying. So there's that identity, or at least that thing that's pretending to be an identity. Multiplication by I actually seems to be pretty decent in that we return everything. We also get a 1 out of it. And then the very last thing is that if I multiply everything by a 1 plus I, it kind of all breaks down. It becomes pretty cruddy in that we don't see a 1, so I have no inverse, and we actually get some repetition. So the weird thing here is that if you take 1 plus I and multiply it by another 1 plus I, they multiply to make 0. And that's something I really don't want to have. Is I don't like having a non-zero thing multiplied by another non-zero thing, and they multiply to make 0. That notion of 0 divisors is really bad. in that it breaks lots of stuff, because I would like to go backwards of being like, if two things multiply together to make a 0, one of the things had to be 0 to start with. This doesn't actually give me that. So what that tells me is that I need another way to do this. This cheap way of just appending an I onto things is great when I look at fields that have 9. It works out really nicely there. It breaks down pretty horribly when I try to look at fields that are going to have 4 elements. So that motivates that we need another way to do this. We can't just do this cheap little complex number trick. We need something else, and we also need to be able to extend this to much larger ideas. So this is looking at 2 to the 2 power, so k is 2. We would really like that to be, 2 to the 10,000 or 2 to some massive exponent. So we need just this much deeper concept to kind of springboard us into a nice way to build these things up. So that's what we're going to do next, is we're going to try to properly build a field with 4 entries, and then look at how we can build a field that are going to have 8 entries, and then any power of 2 that we want to work with.